Fifth graders, lesson 1-9 is factor strings and prime factorization. The objective is I can find the prime factorization of a number. So let's talk about factor strings. A factor string is a multiplication expression that has at least two factors that are greater than 1. So you can see for 24, we have 2 times 3, which would be 6, times 4 equals 24. So there are 3 factors in that factor string. So we say the length of the factor string is 3. Here are all of the other possible ways that you can multiply to get 24 without using the number 1. And remember, we don't want to use the number 1 when we're making factor strings. You can see that the length of each of these is different. And if we look at our factor strings, the length of the factor string is equal to the number of factors in the string. The longest factor string for a number is made up of prime numbers. So that longest factor string, we call that prime factorization. So we're going to take a look at some examples. We're going to make some factor strings for 12, and we want to try to make as many as we can. So let's start with 2 times 2, which is 4, times 3. So the length of this one, 2 times 2 is 4, times 3 is 12. So it equals our number 12. The length would be 3 because there are 3 factors. I could also do 4 times 3 equals 12. I can just have 2 factors. And then the length would be 2. I could do 6 times 2, which is 12. And again, the length would be 2. But if we remember with our factor strings, this longest factor string that has only prime numbers, because 2 and 2 and 3 are all prime, that one is going to be our prime factorization. So you're going to go through and find different ways to make factor strings for each of these numbers, and then write the length of the string, counting up the number of factors it takes to make that number. Another way to find prime factorization without making all of those factor strings is to do what we call factor trees. So we're going to make kind of like a little pine tree here. 27, if I were to break that down, what times what equals 27? Well, I know that 3 times 9 is 27. 3 is a prime number. The only way to make 3 is 1 times 3, so I'm going to circle that. I can break 9 down further though. See how it's like branches of a tree? 3 times 3 equals 9. Now again, I know that 3 is prime, so I'm going to circle these. And now my factor tree is complete. I can't go any further. I'm going to write 3 times 3, so I'm writing out my factor string with all prime numbers. And that is my prime factorization for 27. If I were to do the same thing for 42, I know that 6 times 7 is 42. And there's other ways to do this as well. I could do 2 times 21, and that would work. Okay, so it doesn't always have to be the same multiplication problem that I'm giving you. Any way that you can multiply to get 42, you can break it down. I know that 7 is prime, so I'm going to circle it. 6 is 3 times 2, or 2 times 3. Again, the order doesn't matter as long as we're breaking down our numbers into prime factors. 3 and 2 are both prime, so I'm going to circle those. And now my factor string, or my prime factorization for 42, is 3 times 2 times 7. And again, if I were to check, 3 times 2 is 6, times 7 is 42. And so I get my product. Now we're going to come back to the exponential notation part of this. well, I guess we can do that now. We've talked about exponential notation. It's where you put those exponents on. And so anytime I have a factor that repeats, like 3, 3 is my base. That's my number I'm using. 3 is also up here 1, 2, 3 times. So I could say that this is 3 to the third power, or 3 times 3 times 3. For this one, I don't have any numbers that repeat, so my exponential notation is going to look the same as my prime factorization. You know, if I had a number where there were 2 2's times 3 times 7, then I would use my exponents. But here I don't really need any exponents. Okay, so now we'll take a look at the next page where we use a few more exponents and do some practice. Remember that exponent is the raised number. So here, 5 squared, we have 5 times 5, which is 25. We can read it as 5 squared or 5 to the second power. We also have 10 to the third, which is 10 times 10 times 10, which gives you 1,000. We can also say it's 10 cubed or 10 to the third power. Here we have 2 to the fourth power, or 2 times 2 times 2 times 2. So this is our base. It's the number we're multiplying, and this is how many of those we're multiplying together. So on page 26 in your math journal, if we look at number 3, we're going to be rewriting each number written in exponential notation as a product of factors, and then we're going to find the answer. So in the examples, 2 to the third, we have the number 2 that we're multiplying 3 times. So 2 times 2 times 2. And if I do that, 2 times 2 is 4, times 2 is 8. The other example, we have 2 to the second times 9. So we have two different bases here. 2 is going to appear 2 times. So we have 2 times 2. And then 9 is going to appear just once. And if you multiply 2 times 2, you get 4, times 9 is 36. So let's do a couple of these together. Letter A, we have 10 to the fourth. So my base is 10, and I'm going to multiply that 4 times. So 10 times 10 times 10 times 10. And then I need to find the answer, and I'm going to let you do that part. Let's take a look at letter B. I have 3 to the second times 5. So 3 is going to appear 2 times because it's to the second, so 3 times 3. And then 5 doesn't have an exponent, it's just going to appear once. And so again, I'm going to do 3 times 3, which is 9, times 5, and I'm going to find the answer to that and write it over here. Down below for number 4, now they're giving you the string of numbers. They're giving you the multiplication problem. So 5 times 5 times 5 is 5 to the third, or 5 times 5 times 3 times 3 is 5 to the second times 3 to the second.